Hello, everyone. My name is Dans, and I represent the Institute of Electronics and Computer Science located here in Riga. And I will be telling you about one of devices that we are currently developing, which is meant for high precision measurement of event time and amplitude. So our institute has been working on timers for detecting events for a long time now, and currently we are working on a new device which is called event time and amplitude meter, and our timers have precision of up to 3 picoseconds or less, and this timer will be able to detect event time and amplitude of nanosecond wide pulses. And these timers can be used in satellite laser ranging applications. And one of them is currently employed in RIGA satellite laser ranging station. And these devices employ pulse amplitude measurement technology, which is based on digitization of a peak detected signal. However, these timers have two downsides, one of them being that they are dependent on environmental factors such as temperature, and yeah, that's basically it. In order to detect the time of the event, we use the enhanced event timing principles, which can be seen in this picture. Basically, when an event is detected, a secondary signal is generated, and the secondary signal resembles an isosceles triangle, and this signal is asynchronous to the clock signal, but it is in phase with the event pulse. And then by detecting the phase of our secondary signal, we can deduct what is the time of our event.
Is the secondary signal what you want to measure?
We want to measure the event pulse, and when the pulse happens, we generate.
Okay.
Yeah. Okay. All right. So this is the block diagram of our device that we are currently working on, and it will be able to simultaneously detect event time and amplitude. However, it will be able to do it only for one of the inputs, and yeah, it will have a greatly improved parameter stability in relation to temperature. It will have higher precision, and as you can see, it has an outer 10 megahertz clock input, and this clock has to be very precise in order for the whole device to be precise. There is an option to use the internal clock as well, but then the precision is not guaranteed. And this clock is up converted to 100 megahertz inside the device, which is then used to power digital circuitry like FPGA. And on the user side, the user will be able to change whether the event is in the range of from -2 to 2 volts. If the user can control the threshold voltage, whether the event edge is leading or trailing, and yeah, and so this is the timer we are currently working on, and here is a comparison between our previous timer that we developed and our new timer that we are currently working on. As you can see, there is an improvement of timing precision. There is also a reduction in dead time, in which the timer cannot be used, and as well as this new amplitude measurement circuitry, which will simplify the setup when used in satellite laser ranging applications, as well as it can reduce the costs of timers because the amplitude measurement part is integrated into our system. So this is a picture of one of our amplitude measurement devices. Here is a picture of a one pulse peak detector. And here you can see one of our previous timers. Basically, it consists of three parts: a power supply, a clock generator, and the timer circuitry. And in order to measure what is the precision of our device, we had to conduct an experiment where we would put our timer in a thermal chamber and then change the temperature in this thermal chamber. And based on that, we can deduct what is the random error of our timer. And then by knowing how our random error changes with temperature, we can calibrate our timer for it to be more precise. So basically, we conducted an experiment where here in this graph you can see time, and on y-axis we have the temperature, and with a red line represents the internal temperature of our timer, and the blue line represents the outer temperature. And we started when the thermal chamber was at room temperature around 22 degrees Celsius. Then we increased the temperature to 40 degrees. Then we decreased it to 5 degrees. And this was basically one measurement cycle. And then in this graph, you can see the same elapsed time, but on the y-axis, we have the random error. And so basically, then we can combine both of these graphs. And we get how the internal temperature affects the error of our timer. So the one measurement cycle is represented. It starts with this red color, then it goes way up to 40 degrees outer temperature. Then it is decreased back down to 5 degrees Celsius. And then it's heated back up to room temperature. And as you can see, our timer is most precise in room temperature. And then its random error increases as temperature changes. And this same graph can be drawn in a different way, where now we have the error on the y-axis as well, but on the x-axis we have the slope of our secondary signal that we generated. So when the temperature is below room temperature, that is below 22 degrees, then the slope is similar in its value. And when the temperature is increased above the room temperature, then the error starts, not the error, the slope starts decreasing as the temperature increases. And so, since we did this experiment, we had an idea. Well, we knew what were the errors in different temperatures. And so we had to calibrate our device for it to be precise in different temperatures. And we did that by creating a table which contained information of the slope of our secondary signal and how the slope changes with temperature. However, since we had to have a table for each degree Celsius, there were a lot of tables, and that required a lot of memory, which was a downside and an obstacle. And to deal with this problem, we described the slope of the signals in different temperatures with a polynomial, so that this polynomial can be stored on our timer. And the FC is the calibration function, and then the X is the interpolation signal of the ADC sample reading difference, and then T is the temperature. And yeah, that's the way we calibrate our new timer. And one of our previous timers has been used in a RIGA satellite laser location station. And here are the test setup and results. And our timer is the second one, the ET40, and the timing precision was high, 2.4 picoseconds. And in this case, the environmental factors, the temperature didn't matter because it was stable. And yeah, that's basically it. Thank you for your attention.
Okay. We can one question. Please. Jonas?
When I was young and started to announce transistor, it was very fast, it worked on a 30 kilohertz. When I was freshly graduated student, I had transistors which are operational up to the 30 megahertz. This moment, the fastest what are commercially affordable, about €1 per piece, are 95 gigahertz. It's just 10 picoseconds. How you are connected with this gradual improvement of the components? Do you are following that? Just they are going up straight after you.
Oh, yeah, there might be, but if we use those new transistors, we can get a higher clock, and we can get our system to work
Exactly.
in a higher speed, and then we can make the timer even more precise with this. Yeah. Yeah, I haven't really thought about that. I guess I would have to ask my colleagues. But definitely, yeah, transistors are getting faster, and I guess in this case we focus on the method of when we don't have a transistor as fast as there are. So we need a way to detect these short impulses in some other way without the fast components.
Okay, thank you once more. Now